Okay, hello everybody. Welcome to the next installment of our weekly reading group. This week, I'm very excited to be going through, well, two papers actually. The main paper that we're going through is the era of one-bit LLMs, which is a paper that came out a few weeks ago. But before going through that, I thought it was worth going through the preceding paper, which is BitNet, Scaling One-Bit Transformers for Large Language Models. It's from the same authors, so it's from the same group of researchers from Microsoft Research, the University of Chinese Academy of Sciences, and Tsinghua University, I think might be how you say it. So it's from these researchers here, and then we'll be going through the second paper afterwards, basically. So I guess just kind of starting high level, and also given that we've been changing the system a bit, if we are having any troubles on YouTube, then obviously just let me know, Guillermo or anyone else listening in. But I think I'll assume that it's all working fine. So first of all, starting with a bit of a high level. So obviously large language models have, okay, glad it all sounds good on YouTube, good stuff. So obviously, oh, would you mind muting Chaitanya? Chaitanya, would you mind muting? Thank you very much. Awesome. Okay, so yeah, so basically the high level is that basically, large language models have exploded onto the scene. They're growing in parameter count all the time, and these consume a huge amount of memory. So obviously quantization techniques have been broadly applied not only to transformers, but to CNNs and to all kinds of different machine learning models. And they've been explored for, well, at least the last decade, if not more. But the question that these authors are addressing across these two papers is, can we go to the extreme, and can we do training-aware quantization down to the level of 1 bit in the case of the first paper, or 1.58 bits in the case of the second paper, which basically means 3 states? And can we get comparable performance to the original floating point 16 transformers when doing something as aggressively quantized as 1 bit or 1.58 bit quantization? The high level answer is yes, you can, and the results are actually pretty astounding. I find this to be really interesting, particularly in light of what this might mean for future hardware development, and when you kind of ask these questions about what are the scaling laws and how can you get the maximum performance per unit cost and per unit energy and per unit computation, 1-bit transformers are much more cost, energy, and compute efficient for getting the same performance with much less data, basically. So starting off on a high level then, so the abstract, I think we've kind of got the high level objectives of the paper. So they start out, actually figure 1 isn't referenced in the text, they just kind of throw this out there on the page. So what they're basically showing is that BitNet, compared to lots of post-training quantization techniques, so a very common thing, because it's also a lot easier and you don't need to retrain a large transformer auto-aggressively from scratch, is a lot of research has been done on taking a transformer that has already been trained and then applying post-training techniques to try to squeeze the performance out of the weights. So there's techniques like smooth quant and GPTQ and QIP that are all done where the training bits are 16. So float 16 is what's doing the training. And then inference, they reduce the bits later. So basically what they're saying here is, yeah, you can do floating 0.8, which is also quite commonly used to do training from scratch, but there's not that many other techniques. And BitNet has 1 bit during training and 1 bit during inference, which makes it stand out from these post-training techniques. In terms of the accuracy, so when you do these post-training approaches, in this case, it's quant in particular, quantization post-training with state-of-the-art methods, you typically get massive diminishing returns in terms of the quality you can get, with random being here. So by the time you get to 1 bit, you're really not doing much better than random, whereas BitNet is out here, on its own with much better performance than the post-training quantization techniques. What they show here is that the energy cost reduction ratio actually increases with model size. So you start off at 100 million parameters, getting about a 9 times reduction in energy cost ratio, whereas when you get to 30 billion, you end up with almost a 40 times reduction. So this is increasingly relevant as the models get larger and larger. So again, incredibly relevant as we're scaling into the future with trillion parameter models and so on. And here they show that they have a scaling law. So what they're actually showing here is that when you fit a simple polynomial to the first kind of 6 data points, and then you expand that polynomial, you can with high accuracy predict the end overall loss of I think this is maybe a 13 billion parameter model and a 30 billion parameter model with very, very high accuracy. So we have this very predictable scaling law that exists not only for floating point training, but also for this this quantized training as well. So, I mean, kind of the introduction I broadly covered, I think, in the description. They have this quote just kind of out of nowhere from William Henry Gates III that says, "I don't think there's anything unique about human intelligence. All the neurons in the brain that make up perceptions and emotions operate in a binary fashion." So I guess giving more relevance to this very old quote. And again, maybe kind of taken as a step in the direction of the way that we understand that neurons actually work, which is by and large, obviously they do have strengths, but a lot of research on the brain does suggest that the neurons do act in a relatively kind of on and off fashion, and it's much more a kind of binary signal than actually the weights of the neurons. So I think that is also interesting that there might be some parallels to how the brain, I mean, very loose parallels to how the brain is incredibly computationally efficient while also incredibly vast. So there's like a tiny percentage of the brain used at any point in time in a very data efficient way. There is a loose analogy to what we're seeing with mixture of experts, which is taking a step in the direction of only using a subset of the weights at any point in time. Obviously, with a mixture of experts, you're using maybe 10% of the weights on any given moment. And now with the 1 bit, we're seeing that actually this again suggests that bigger networks with a smaller representational capacity is better. So we're taking increasing steps towards massive networks where there's very memory efficient representations and only parts of the network used at any point in time with mixture of experts. So all of this is actually taking steps directly to what we know about how the brain works, which I also find super interesting. So now explaining how BitNet works on a high level. So basically, it's very simple. You take the original transformer architecture and you are basically replacing the linear layers with what they call this bit linear layer. So everything else remains the same. They actually have int8 quantization in the input, so the activation. So there is actually some quantization there as well, where they don't use float 16. But the most important point is that all of the torch NN linear layers are replaced with this bit linear layer instead, basically. So what does the bit linear layer do? So I guess what I can do, well, let's go, so we can come back to the image in a moment. Let's first go through the maths in the order that they go through, because I think that's a good way of starting. But on a high level, you can imagine that what you have is you have your weights, as is always the case with quantization-aware training. So you do store the weights in their full precision, kind of latently, because obviously you need somewhere for the weights to propagate their gradient updates. But then during the forward pass, you effectively go through some operations to binarize the weights, to basically flip them into their, in this case, +1 and -1 states. So in this case, in the first paper, they clip everything to +1 and -1 in the weights. Whereas in the second paper, they do +1, 0, and -1. But for now, they basically take the weights, they get them into this +1, -1 state. They then have also quantized the activation so that they are within this, well, basically within this integer range up to 2 to the power of bits -1 and down to -2 to the power of bits -1, basically in the integer quantized range. And then they do the quantized matrix multiplication here, and then they bring it back into the original scaling by using a kind of activation-based scaling and a weight-based scaling so that it can then continue outside of this quantized realm. High level, that's what's going on. But let's go through the steps one at a time, because there are some nuances here. So what it says is, as shown in figure 2, BitNet uses the same layout as transformers. So this is here. stacking blocks of self-attention and feed-forward networks. Compared with vanilla transformer, BitNet uses bit linear. So this is this instead of the linear layer. Instead of the conventional matrix multiplication, it employs binarized 1-bit model weights. We leave the other components high precision. So they use 8 bits in their experiments for the activations. They summarize the reasons as follows. First, the residual connections and the layer normalization contribute negligible computation costs, the large models. So that's why they focus all of their quantization efforts just on these map models. So it's just these linear feed-forward sections that they quantize, and everything else they don't. Secondly, the computation cost of the QKV transformation is much smaller than the parametric projection as the model grows larger. So again, they're really trying to cut down on this thing that scales, quadratically with the context length. And third, they preserve the precision for the input-output embedding, because the language model has to use high precision probabilities to perform sampling. So they don't want to make the activations 1-bit as well. They need to keep some kind of continuous representation, which is why the outputs and the activations remain 8-bit, and it's just the weights that go all the way down to 1-bit, basically. So that's kind of the rationale behind their decisions for which parts to quantize to 1-bit and which bits to keep 8-bit. No pun intended. Okay, so they first binarize the weights to either +1 or -1. They're using this signum function, which is, as the name suggests, just the sign of the number, basically. So the signum is simply +1 if the magnitude is greater than 0, and -1 if it's greater than or equal to 0. I guess the equal to could go on either side, but yeah, and they need to put it somewhere. So basically, this is the function. They centralize the weights to be 0 mean before the binarization to increase the capacity with a limited numerical range. So you imagine you initialize these weights using Javier initialization or whatever. You then offset it by the mean so that it's 0 meaned, and then you do this signum function to binarize the weights, basically. So that's what the first do. They then get the scaling factor beta used after binarization to reduce the L2 error between the real valued and the binarized weights. So there's then the scaling factor that means that effectively you scale, if I'm understanding that correctly, you effectively scale it so that the plus and -1, you basically then have them scaled to be plus or minus the standard deviation, which is how you would reduce the L2 error between the real valued and binarized weights. So you basically kind of scale it accordingly. Yeah, and then they can be formulated as follows. So you basically take your initial weights, which do remain. So this is one thing that I was having to think about a bit, but basically the actual real floating point valued weights remain in memory during training and everything. You have this operation to binarize them, which is this minus the mean of the weights, do your signum function, which is described here. And then, yeah, alpha is just the mean. It's just the sum over both matrix dimensions, well, the sum of all weight elements divided by the number of elements in the matrix, basically. Okay, so that's that. So then they further quantize activations to B-bit precision. So they use this absolute max quantization, which basically scales the activations into the range minus Q sub B. Q sub B, where Q sub B is 2 to the power of B minus 1. Obviously, this is just kind of, you can think about the way you would typically have a signed integer range. So basically, this is the range of a signed integer with B number of bits. So then they multiply, and they use that, which scales activations in this range, and they do that by multiplying with QB and dividing by the absolute maximum of the input matrix. So yeah, so this is what we're explaining here. So in the image, we have this abs max quantization. This box is described by this line, and basically we do the quantization, which is to clip the raw floating point, or the raw values scaled by this. Obviously, you basically just rescale the maximum that's observed to actually correspond to the maximum in your range, and then you clip your min and max to the minimum value in the new range and the maximum value plus some small amount to avoid overflow errors. So again, very simple, and I think we all know how the clip function works, just a max min. And yeah, and this is the the maximum absolute value. Does it say that somewhere? But I think it's basically, yeah, by dividing by the absolute maximum value of the input matrix, which is what this is. Yeah. And yeah, eta is just, I think it's eta. It's just a small floating point number that prevents overflow when performing the clipping. I always get the Greek letters wrong and just end up saying what they look like in English letters, which is a bit ignorant of me. But okay, so then for the activations before the nonlinear functions, we scale them into. So this is something that's interesting. Actually, they don't do this on the subsequent paper, the 1.58-bit paper. But I thought it was a bit weird because then you don't get the clipping of ReLU. But I guess their point is that actually, because everything is going to be +1 or -1 anyway, everything is relevant. There's nothing that's 0. And therefore, you want everything to go through the ReLU and not be clipped by the kind of, 0 when the value is less. So I'm not sure exactly, but basically, if the activation is before the nonlinear functions, instead of scaling them to minus Q sub B and Q sub B, they do it to 0 and Q sub B. Yeah, by subtracting the minimum of the input so that all values are non-negative, basically. So yeah, they just do this. So they just, yeah. So basically, yeah, remove that so everything's positive and do the same thing, basically, when they're doing the quantization before a ReLU layer. Okay, simple. So again, they quantize the activation to 8-bit and they leave it to future work to do lower precisions, although actually they keep 8-bit on the next piece of work. So I guess that's not actually what they do in future work. Moreover, the quantization is performed per tensor during training, while it's per token during inference. Yeah, that makes sense. With the above quantization equations, the matrix multiplication is as follows. So now we have your the 1-bit quantized weights multiplied by the 8-bit quantized activations. So this Y corresponds to this section here, or this line here. So we have our 1-bit quantized weights coming in. We have our, so, they could probably have added W hat here to make it clearer, and X hat here to make it clearer, but basically Y is here, this bit, in the entire box. So they get that. The matrix multiplication can be written as follows. They assume the elements in the weights and the activations are mutually independent and share the same distribution, and that they are independent of each other, and therefore the variance of the output Y can be estimated as follows. So it's the variance of the multiplication, but because they're independent, this can just be n times the independent variances, and then they can take beta squared out because of some reason, because that's just the scaling factor of the weights. Yeah. I can't remember why this is actually. Maybe because we know the variance is 1. Yeah, I think that's it. Oh no, because it's, yeah, because this is now 1, so this reduces to beta squared. And yeah, okay, exactly. So this be reduced to beta squared, and then we have this, which is I can't remember why exactly, but I think because, I don't know, these are roughly equal to 1. I can't remember exactly why this is the case, actually. If anyone knows, then feel free to let me know. But basically, they come to the conclusion that the variance of Y, so the variance of this output here, is approximately equal to this, the expected value of their quantized activation squared. They then say for the full precision computation, the variance of the output is at the scale of 1 with the standard initialization method. So actually that's true. So if you do Javier initialization, the non-quantized standard deviation is 1. So to preserve the variance after quantization, they introduce a layer norm function before the activation quantization. In this way, the variance of the output Y can then be estimated as follows. So the expected value of now the layer norm applied to X squared, which is equal to 1 because of the layer normalization, basically, which then has a set magnitude of the full precision counterpart. So I kind of loosely follow that. Basically, when you do layer normalization, you make the expected value of this equal to 1 because it's normalized accordingly. So then it brings us back to the expected full precision counterpart of Y, which is 1 due to the standard initialization methods of Javier and so on. So basically, TLDR, this layer normalization here is helpful to make sure that the standard deviation of the output here is going to be the same as what we would expect us to have if we weren't doing non-quantized output, basically. And that's what this layer norm is serving to achieve. Cool. So, yeah. And this is basically actually already a known thing. So when you have this layer norm before the matrix multiplication, it's called sub-layer norm. It's actually an explored technique which has various benefits in and of itself. So with sub-layer norm used to correct the standard deviation of y, and with the quantization methods, they then finally have the full bit linear layer, which can be formulated as follows. So actually now y, which is a bit confusing, y now means the output of the entire thing, whereas here it meant the output of something else. And also x now means something else now, because x here meant x hat meant quant x, and now x hat means quant x layer norm. So they kind of repurpose the variables, which is a little bit confusing, but yeah. So now we're referring to the entire process. So basically, the way you get x hat is by doing both of these operations. So it's now referring to both of these, and not just the first one. And we then include the scaling as well that's done at the end. So again, the way that this corresponds to the diagram is that we have the first block at the bottom, the second block, the matrix multiplication represented by the x, and then we have these scaling parameters done as well at the end. So again, I've been nice about both of these, but yeah, we have the first block, the second block. The beta is calculated based on the statistics of the weights. Again, for recap, beta is, where is beta described? Yeah, it's basically the kind of standard deviation of the weights. It's used to reduce L2 error between the quantized and the real one. So if I'm not mistaken, it is just the standard deviation, I think. I don't know why they don't say that. But yeah, anyway, beta is calculated from the weights, and this is calculated from it's the maximum absolute value of the activation. Yeah, the absolute maximum value. Yeah. Anyway, so that's what we get, and then we just basically need to scale it by these, divide by this, and then we get the output again. And the layer norm is described as follows. And again, yeah, it was actually here. Beta is the oh yeah, no, sorry, beta is the mean of the weight. Sorry, yeah. The mean absolute, yeah, okay. The mean absolute value of the weights. Yeah, makes sense. Cool. Okay. Yeah. So, which is almost going to be the standard deviation, because if there's as many positive and negative, then I think it's the same. Oh no, maybe not. Anyway, it's this. It's this basically. So then we have this full bit linear, and yeah, and that's basically it. That's basically how bit linear is formulated. I've gone through that quite quickly. Any thoughts, questions, comments from anyone before I keep going? I know I talk a bit quick. Otherwise, I'll keep blasting through. There was a few areas where I didn't do a great job of deriving this, but I think that's okay. We get the idea. Basically, the layer norm is needed to get the standard deviation into the correct position. Yeah, but everything else makes sense. Okay, well, if there's no questions, I'll keep going through. Also, obviously, if there's any YouTube questions, I'll check at the end. So yeah, then so one thing that's important here is that often when you're training these large models, you need to do model parallelism across many devices, because these matrices become very large. You can very rarely compute the entire matrix on a single device. So they say one essential technique to scale up large models is a model parallelism, where they partition the matrix multiplication onto multiple devices. A prerequisite for this is that generally the tensors are independent along the partition dimension. That obviously helps, because then you don't need to synchronize statistics across all of these devices, and each of the devices can compute their, do their work independently without needing to do synchronous communication bottlenecks. But unfortunately here, there are these parameters, alpha, beta, gamma, and I forgot what this is. All of these parameters are calculated from the whole tensors, breaking the independent prerequisite. One solution is to introduce one all reduce operation for each parameter, but of course that requires a kind of synchronous communication pass across the devices, which can hurt performance when the quicker devices are then left waiting and can't keep churning through their work asynchronously. However, even though the communication for each parameter is small, the amount of synchronization grows as the model becomes deeper, which significantly slows down the forward pass. The problem also exists in the sublayer norm, where the mean and the variance should ideally be estimated across the entire matrix, so across the partition dimension. So to this end, they propose the simplest solution you can imagine, which is basically to just treat the statistics in isolation with the components of the activation and the weight matrix that are available on the particular device. So they basically they divide the weights and activations into groups, and then they independently estimate each group's parameters. This way, the parameters can be calculated locally without requiring these synchronous communication passes. So yeah, it's called group quantization, and it's formulated as follows. So, I mean, again, I don't know if we need the maths, it's pretty straightforward, but for each weight, they divide it into G groups along these partition dimensions, and each group has size of n over G times M. So they partition along the n dimensional matrix. And then they estimate the parameters for each group independently, basically. And it's as simple as that. Yeah. They do the same for the activations, into groups again. They do the same for layer norm. Let's compute the mean and variance. Yeah. So basically, they just do it per group, and they can do the model parallelism with grouped quantization and normalization with no communication overhead required. So they can keep things running quickly and asynchronously. Well, relatively speaking, obviously, you still then need to get the matmul back, and there's going to be points where synchronization is needed, but there's just less of these points where you need this kind of synchronous back and forth communication. Okay, so then they talk about model training. So yeah, they use the straight-through estimator, which basically means that any non-differentiable components are kind of ignored. So it's the same as what you would do if you have a max pool operation, for example, when you were doing CNNs many years ago. One way of doing image reduction would be to take a grid of 4 values and take the largest value, and then during the backward pass, you ignore the other 3 values, and you just assume that the graph only connected to the largest value. So you do this kind of like conditional evaluation on the forward pass, and the backward pass assumes that graph to be locked in place. This is what they do here. So to train their 1-bit model, they employ the straight-through estimator to approximate the gradient during backpropagation. So it basically bypasses all of the non-differentiable functions, such as the sine function that clips. I mean, the biggest one here is the sine function that's effectively taking your continuous valued weights and clipping them to 2 values. So this is a very non-differentiable function, obviously, and they just assume that the graph connects to whichever one it was connected to, and then also the clip function as well is non-differentiable, and again they use the same approach. So the straight-through estimator allows gradients to flow through the network without being affected by these non-differentiable functions. Again, this is just how you train any model that includes non-differentiable kind of step functions. So then on mixed precision training, so the weights and the activations are quantized to low precision. The gradients and the optimizer states are stored in high precision to ensure training stability and accuracy. And following previous work, which I think is kind of the only way you could do this, so it's kind of implicit, I think. But what they do is they maintain a latent weight in the high precision format for the learnable parameters to accumulate the parameter update. So I guess it's floating point 16, or it could even be floating point 32, but I assume 16 are preserved in memory, and that's where the Adam optimizer gradient updates are applied, and these latent weights are binarized on the fly during the forward pass, but of course they're then never used for inference. So while you need them for training, at inference, obviously, the entire capacity of the network is dictated by the quantized weights, because that's what is a fundamental part of the forward pass, basically. So you can discard the real high accuracy weights after the training process. Yeah, so the learning rate, they say that one challenge for the optimization is that, which is, again, as you can imagine, one challenge for the optimization is that a small update on the latent weights makes no difference to the 1-bit weight. So you have 3.75, and then you do a gradient update and it becomes 3.72. As far as your forward pass is concerned, it's still just 1. And you're not going to notice that the network is now performing differently on the same input data as it was previously. Of course, things like atom momentum can kind of keep it moving in that direction, but you then get this kind of you then get this discontinuity where suddenly you're going to have these step moments where the output of the network looks very different, because all the weight can do is suddenly, after many gradient steps in the latent weight, it's suddenly going to flip from a 1 to a -1. It's going to quite drastically change the output, and you're not going to get this smooth change in the outputs of the model as you're making these gradient steps. So the way they say they overcome that, because otherwise if you have a small learning rate, it's just not going to, the changes in the weights aren't going to happen quick enough. Basically what they do is, so it's even worse at the beginning of training, because the very beginning of training, you're taking these random initialized weights and typically, very quickly learning very simple patterns before then learning the harder stuff. And you need the weights to be expressive enough to learn these things quickly. So it's worse at the beginning of training, where they're supposed to converge as fast as possible. To address this challenge, they explored methods, and they concluded that simply increasing the learning rate is the best way to do this. They show that BitNet benefits from a large learning rate for convergence, while the floating point 16 transformer diverges with the same learning rate. So, and they give some results on this. So that's how they overcome this kind of discontinuity problem. I would have thought there's more interesting ways you can overcome this potentially. Maybe there's going to be some interesting research here, but it does seem like a bit of a problem. But I mean, I say that. I mean, the results speak themselves, so I guess it's not that much of a problem. So they then estimate the computational efficiency of BitNet in terms of arithmetic operations and memory footprint. They focus on the calculation for the weight matrix for the matrix multiplication, because it contributes most of the cost to the large language models. So basically the point here is that the arithmetic operations energy is a lot lower. So they assess this both for different process node sizes, so 45 nanometer and 7 nanometer. And with floating point 32, you have 0.9, 0.38, and then you have 30 times lower with your intake. So basically much more energy efficient. In linear transformers for matrix multiplication with dimension m times n, the energy consumption is as follows. The main point here is that they don't need to do, well, they need to do very few multiplications. Because you now have +1 and -1, your matrix multiplication reduces to a long list of additions. So because you have all these, and also in processors and CPUs and so on, matmul, or multiplication, sorry, is a much more expensive operation than addition. And now because we've removed the vast majority of the multiplication operations and it's all now reduced to addition, things are substantially more efficient and also faster as well. So the energy consumption is dominated by the addition operations as the weights of 1 bit. The multiplication operations are only applied to scale the output with the scalars beta and gamma over q sub b. So the energy consumption for multiplication can be computed as follows, which is significantly smaller than transformers because of the domination of addition and the removal of multiplication. So basically a lot more energy efficient, which is great. They then compare with floating point 16 transformers and basically get very comparable results with a much smaller cost, memory, and much faster as well. So the first thing to look at is, is there a predictable scaling law? So do we get the same thing with the BitNet as well? So they start by plotting the scaling of both BitNet and floating point 16 transformers with a fixed number of training tokens, and they show this in figure 3, showing that the loss scaling of BitNet is similar to that of a floating point 16 transformer. So in figure 3, they have that shown here. So BitNet, the loss goes down with much smaller inference energy, and also with model size. Obviously, the loss doesn't, it's not as good as a floating point 16 transformer for the same number of parameters, because the parameters are more expressive. But actually, as you start to get to bigger models, this gap decreases. So, the difference at 100 billion is a lot less than the difference at, say, 100 million. So you really start to see diminishing returns of having this floating point 16 as you get to very large models, which of course is the only thing that really matters as computers are getting, as hardware is getting bigger, models getting more performance. This is the regime that's really relevant for, the years ahead. So very, very interesting and very, very compelling results. So they show that. They show various things. We don't need to read through all of this. We can kind of look at the graph. So they show, because I also want to go through the second paper a bit as well. They show that inference energy consumption. So BitNet consumes a lot less energy, getting very good accuracy. They do this on kind of 4 different downstream tasks. Same here. So this is 0 shot and few shots on 4 different tasks they talk about. I think they do it on what are they on? They do it on these Hella Swag, Winner Grande, and Story Close. So just some various tasks, and they do 1 shot. Sorry, 0 shot means the prompt just contains the question, and few shot means that the prompt contains several examples before you then ask the final question. And again, basically, much lower energy, kind of energy accuracy trade-off is much better with BitNet. They then show here, which I thought was a little bit cherry-picked, to kind of, they make us, I don't know, it was a slightly grandiose thing to, maybe not grandiose, but maybe overstretching a bit to say that, well, I don't know, maybe not, but I don't think it was compelling just to show up for 1 learning rate. They say that BitNet is more stable than floating point transformer with the same learning rate, but that's a very high learning rate that BitNet is known to do better with. And actually they had a problem at lower learning rates, it seemed, for BitNet to learn that well. So although it does learn a bit okay here, so I guess learning rate 2 e to the minus 4. I wonder how it did with kind of e to the minus 5 or something. It seemed as though a low learning rate was damaging for BitNet based on how they articulated the need for the high learning rate before. So I wonder if there are any learning rates where BitNet is less robust than floating point 16. Maybe not enough graphs to tell convincingly, but either way, I mean, it is interesting that on these higher learning rates, the F16 totally catastrophically fails. It's too high, whereas BitNet is able to be stable at this higher learning rate. So yeah, interesting to explore why that is exactly. Cool. So then they do, so some comparisons with post-training quantization. Again, I'm just going to blast through the graphs. They have a full transformer with full floating point 16 everywhere. BitNet, which has weights 1 bit, activations 8 bit. So these are the 2 at the top. And then various other approaches with both 4 bit, with 2 bit, 16 bit, 2 bit, 16 bit. Again, W meaning weights, A meaning activations. And again, the main story is, and these are on tasks. So this isn't looking at the validation loss or anything. This is using the model on new tasks across these 4 data sets again. And yeah, the BitNet is much better, much closer to the full transformer than any of the other post-training methods. Same here. So they show lots of different methods, which include post-training quantization. Obviously, this is the full transformer without any post-training quantization, and then various post-training methods, and then BitNet again, which is not post-training. And they show the perplexity and then the performance on these 4 data sets that we talked about, as well as the average. And yeah, the perplexity is good when it's low, so it's not as good as the full transformer, but much better than anything else. Actually, I mean, so this one is better, but this is again 4 bits instead of 4 bits instead of 1 bit. This one's better again, but again 8 bits, so 8 times the memory. So this is, you know, very good at the very compelling result. And similar here, higher is better on all of these. And again, it's not as high as, well, no, not quite as high as this, but better than all these actually. So again, it depends on the task a bit. These 2 are better than on this one, but again, like in terms of the regime of being 1 bit, I guess one of the takeaways is that all of these are, you know, this is the main one to compare with because this is 1 bit post training, and you know this is much better than anything in the table above, in the column, in the row above. And then they do so what they do here, BitNet on the same again, and they do various other like ablations on the BitNet architecture. So one of them is a different type of activation quantization instead of the 8-bit, and then also BMT. I forgot what the BMT means actually, but there are different ways of doing. So there are different ways of doing layer norm. They do pre-layer norm instead of their sub-layer norm that they've adopted. Yeah, I mean, what's pre-layer norm is different, and BMT, I'm not sure exactly, to be honest. I didn't have time to dive into these too much, but other ways of doing the quantization and the normalization, that their one that they chose in the end was better, basically. Okay, conclusion of future work. Well, we don't even need to read this because we have the future work to go through as well. So thankfully, I know we've kind of gone through 3/4 of the talk. Basically, all of the meat was in this original paper that I only realized this morning. The follow-on paper is almost just like a few extensions to this and some results. So hopefully we've gone through the core concepts. I'm now gonna get the other paper up, which is here. So, oh no, yeah, exactly. So we don't have the abstract, we understand the high level motivation as same as before. They actually show some nice images here just to get the message across more. So, you know, you have the transformers with all these floating points. Their basic point here is we can get the same performance. So before with the BitNet, they had slightly worse. They're actually getting the same performance now with this tertiary approach and much cheaper, basically. And they then show this, again, slightly funny image where they have the floating 16, the 1.58 bits here, and then obviously, again, this point that it's multiplication then addition, because you have all of these multiplications to do, whereas with BitNet, it's just additions. And they're really saying that this warrants a new paradigm of totally new hardware that's really good at doing lots of additions. It doesn't need to be good at doing MapMul, it just needs to be good at doing these chains of additions. And because of the scaling laws they see, this is the way that LLM should be trained. And I tend to agree. I think it's really, really impressive. So again, calls for actions to design new hardware optimized for 1-bit LLMs where it's this very addition-dominated domain. Again, introduction, we kind of know the context. So it's based on the BitNet. Again, they replace the linear. So what are the differences? They use 8-bit again, as before. Now they have a 0 as well, instead of just 1 and -1. So they now adopt the app's mean quantization function, which is, as you would expect, it first scales the weight matrix by its average absolute value, same as before. And then they round each value to the nearest integer among these. So, well, it's almost the same as before. Obviously, before it was apps, like, what was it called? Like sine sum or whatever. Like, it would basically take the sine of the weight and that's it. What they're actually doing now is obviously they're rounding it. So 0.5 would go to +1, like 0.49 would go to 0, and so on. Yeah, so they do this. And they clip it as well to -1 and +1. So that, I mean, that's the same as rounding to the nearest of these values, obviously. Yeah. And this is now the mean. Oh no, that was different. Yeah, they're reusing the terminology across the papers, but this is now the mean of the weights. Whereas before that was the maximum of the activation, so a little bit confusing again. The quantization function, so again, that they remove this clipping, they remove this 8-bit quantization to the 0 Q sub B range, and they instead use quantization to the -Q sub B, Q sub B for everything. So they don't treat the activations before a nonlinear activation differently. They do it the same in all of them. Yeah. And it has negligible effect and it makes the system easier to implement. They use llama-like components because they do a lot of ablations against llama. So they do all the llama stuff we did in the previous llama paper. So it uses RMS norm, uses swigglue, the rotary embeddings, removes all the biases. So in this way, BitNet 1.58, it can be integrated into popular software and so on with minimal effort. So they dive straight into results. That's it. That's the method. It's just the same as BitNet before, but with like these two tiny differences. So I mean, let's just go into the graphs again. I know we have like 10 minutes and I want to get a bit of time for questions, but like, I don't think we need to read, like we understand broadly the kind of experiments they're testing. It's the same kind of data sets. So what are the results? So basically, they look at the decoding latency on the left and the memory consumption on the right of BitNet against Llama with varying model sizes. So again, what we see is that as the model gets bigger, the difference gets stronger. So the speed improvements are more dramatic at larger model sizes, so 4 times faster, and you know, compared to 1.6 times faster as the model grows. And then in terms of memory usage, again, 7 times less memory compared to 3 times less memory. And again, as these scale up, it's only going to get more dramatic. So I think this is incredibly relevant for the very large models, and I wouldn't be surprised if if GPT-4 and so on is perhaps using things like this. I know they're driving the inference cost down, and it's at like 1 point something trillion parameter model. Also, this is researched by Microsoft. I don't know if there's any overlap there, but probably not. Yeah, I'm sure this is the regime that all large language models are going to be adopting if they're not already. So, and interestingly here, actually, I think this is where new hardware becomes very interesting because particularly with the memory, they mention it somewhere, but this is all using a 2-bit, like 2 bits per weight, because there isn't such a way of representing 1.58 bits. So you're actually using kind of, yeah, I don't know, 50% or so, well, no, a bit less than that, but using more, 30% more memory than you need to be using. So if you could find a way to actually, fundamentally represent these 3 values in an elegant way on the silicon itself, then there's even bigger gains to be made without misusing this bit. Also makes me wonder why they maybe didn't try. But no, yeah, I was gonna say it makes me wonder why they didn't try to have 4 values given they've got the memory. But actually, the whole point of the 0 is that you can ignore and filter values. So you need the 0, and then if you need the 0, anything else would be asymmetrical. So yeah, I think that makes sense. Yeah, so then, yeah, so the throughput again, well, they talk about this because of a fixed memory. So assuming that you're on one particular hardware, might have been an A100, I can't remember. Yeah, but they test it on some, you can read through the details, but they test it on one fixed hardware, and because there's so much less memory, they can massively increase the batch size to 176 instead of 16, and that corresponds to an overall throughput increase of 11 times, and they can get 9 times more tokens per second. Again, it makes you think about kind of maybe what Grok might be doing behind the scenes, that there might be some of this kind of stuff going on there as well. So yeah, we've got those. Let's get some more results. They show the energy again versus model size again versus llama. So again, the energy reduction at 70B is 42 times less. So really impressive. This is the energy consumption of one operation, I think. So the llama operation has these floating 0.16 multiplications and these floating 0.16 additions, and actually the entire operation for BitNet is heavily dominated by the int8 additions, which is what they use for the activation representation, and is 71 times less per these matrix multiplications. The reason we don't see 71 times here is because the entire network contains other sections that are not quantized. Again, they're just quantizing these matmulls, but they're very dominant. So even though you get 71 here on the actual operations themselves, the overall network is still 41 times more energy efficient. So really seeing it come through. They show that you can train it on 2 trillion tokens basically, and you get good performance. So it can be basically, there's not a fundamental limit. I guess their point was you can keep training and the performance keeps getting better. If you train it for a very, very long time, the network can keep absorbing the knowledge, and there's no kind of fundamental limit, it seemingly, from having this quantized representation. They talk about enabling a new scaling law with respect to model performance and inference costs, and they just have a few, they do give a few different examples where a 13 billion parameter BitNet is more efficient in terms of latency, memory usage, and any consumption than a 3 billion LLM. So basically, you can, you can have 4 times as many parameters, no noticeable loss in performance, and it's much it's actually cheaper and faster and better than a much smaller model at floating 16. And again, they make similar comparisons with other model sizes as well. This is describing the training on 2 trillion tokens that they show here. Again, I'm going through a little bit quicker now just so the video is not too long. And then talk about discussions and future work. So there's not that many results here. It's basically just kind of saying that they're, because I guess I didn't go through these fully. Yeah, sorry, let me just quickly go through these tables. So this is actually the quality. So they look at the perplexity as well as the cost compared to llama. So yeah, this is what they have. So well, this is about perplexity. So the lower, the better. And they basically show that while BitNet is not as good as llama at the 3 billion size, and same at the 1.3 billion size, quite. And again, not quite as good. It's incredibly close. I mean, these are basically indistinguishable. at the same model size. These are pretty much indistinguishable at the same model size. These are pretty much indistinguishable. Oh, this is better. Yeah, so it has better perplexity at the same model size. And then if you increase it by a small amount, you get a noticeable difference again. So this is really where this kind of original high-level graph that says just as good, like really impressive, just as good as Llama, but much less, much less memory, much cheaper, and so on. And also, just to explain, this is not the pre-trained Llama. The way they do this is they retrain both of them on the pajama data set from scratch. So yeah, they're like fair test, 2 networks. They add all the Llama stuff to make sure it's a totally fair test, so that the only difference between these 2 networks is one of them has the bit operation and the other one doesn't. Other than that, they both look like Llamas basically. And they train them both from scratch and on this data set and see what you get. So it's a very fair test and it isn't distorted by Llama's data set or whatever. And then they get very good performance. So we looked at the perplexity, then they look at these various tasks, and again, yeah, they get very good performance. Beating Llama actually on the 0-shot accuracy in several cases. And even if they don't beat it on the 3B, increasing the parameters by a bit consistently does beat it. And again, is obviously much more computationally efficient. Yeah, so I'm really sold by this. I think it's really interesting, and I assume there'll be hardware startups and companies that have been kind of racing to add ASIC architectures and designs that can deal with 1-bit operations in a really good way, because it seems like the scaling laws that you see here are much more compelling. If you assume that you can get the same performance and something that looks like this in terms of its scaling instead of this, then it's a no-brainer really. So I guess that's what inference of LLMs is going to look like into the future. They talk about mixture of experts being a really interesting area of future research. Yeah, so while it significantly reduces the computation flops, the high memory consumption and interchip communication for all of the different experts on different devices limits its deployment and application. And because of the massive memory reduction, the reduced memory footprint makes the device writing much quicker and easier, reduces the overhead of transferring activations across the networks. And again, if it's all on the same chip, because it's been quantized so much, then you can really make mixture of experts much faster, removing the need to have multiple chips. Yeah, so they talk about the KV cache. So one of the major challenges for long sequence inference is the memory consumption by the KV cache. We had a bit about this, obviously, discussed with the graph call last week. This represents a significant step towards native support for very long sequences, as it reduces the activations from 16 to 8 bits. So you can double the context length with the same resources. And again, they say this can be losslessly compressed to 4 bits or even lower, which delivers future work. So I'm interested by that. If they can, then that'd be really impressive. Obviously, this opens up lots for the edge and mobile, because again, very fast, very cheap hardware, very relevant for CPUs as well, given it's now addition, very much addition focused, that the computational overhead is massively reduced and you can run this on phones and things. So very interesting work for that reason. And again, they really say recent work like Grok has demonstrated promising results and great potential for building specific hardware. Going one step further, they envision and call for action to design new hardware and systems specifically optimized for 1-bit LLMs, given the new computation paradigm that has been enabled by BitNet. And I think that's yeah, I think that's what we will see. I can only assume that well, it probably even something else, because the research isn't going to stop, but at the very least we're going to be having 1-bit or 1.58-bit LLM inference as the default, in the months to come. Yeah, so I found this paper really interesting, basically. I've gone through it relatively fast. I have a habit to talk quite quick. Hopefully it made sense. I do think it was better to go through the first paper first, because this paper is pretty much empty on content, aside from saying we did these 2 things differently from the original paper and then present a load of results. So hopefully going through the basics was a good starting point. Yeah, well, if people were able to follow along at all, are there any questions in the room at all? Or I don't know if people are watching on YouTube, potentially any questions there. Did they use custom GPUs to train the 1-bit LLM? No, they just trained. I think they used. I mean, let me have a look. I think they just use A100s or something. What do they do? Because the runtime. Yeah, well, they do these experiments on A100 cards, so I assume they just train it on a load of A100s. I think in the first paper they mentioned that they train it on like I don't know, a few thousand A100 GPUs, I think. Yeah. Any other questions from anyone at all? I always like to assume that if there's not, then it's because everything's been explained perfectly. But that might be wishful thinking. Okay, well, if not, then what I can say is obviously anybody that wants to dive into this more and ask any of the questions, then of course the papers channel on our papers in our Discord. So we had a bit of a Discord restructure recently, but now under the Learn category, we have a papers channel, and that's where we make all the reading group announcement and where people can ask questions. So we got a question on YouTube. So is the document with which you're lecturing a research project by Ivy, and can collaborators contribute to research papers? So I wish. It's not. It's well, it is a research project, but it's not ours. It was by, I should give credit, it's by these guys. So I'm not going to butcher all their names, but yeah, I mean, Shuming Ma, Hongyu Wang, I say as I continue to butcher their names, and co-authors from Microsoft Research, University of Chinese Academy of Sciences. So yeah, these are the authors. But yeah, I think most of the papers we do in this reading group won't be ours. Maybe one day we'll have an amazing paper to present from ourselves, but for now it's mainly from other people in the field. Yeah. Cool. Okay, well, we're at time, so I guess now's a good time to wrap up. As always, thank you very much for watching, everybody. As always, happy to answer questions in the Discord, of course. I found this paper really amazing. I think it says a lot for where the field is going to go in terms of LLM deployment. So very exciting times, I think. Next week we have, what do we have next week? I'm not sure. Let me quickly check. Next week we have next week we're welcoming Nicholas Mooningoff, who will be presenting his amazing work on generative representation instruction tuning, aka GRIT. So yeah, stay tuned for that one. Very excited to welcome him next week. But in the meantime, hope everyone has a great great Friday, great weekend. Thank you very much, everybody. Bye for now. Bye bye.